righty, so let me get us going. Now, when we talk about the laws of thermodynamics, they're smeared out all over the place. Okay, so it's not just like one concise location to talk about these things. So there's the zeroth law is in chapter 14, the first law is in 15, the second law is in 16. So I mean, it's smeared out over all sorts of places. So we're going to start off with discussing the zeroth law of thermodynamics. And you're like, zeroth law? That seems odd. And let me remind you that we didn't have a good model for heat to begin with. And having a zeroth law is part of that content, which is that we'd already had the first three laws of thermo, and none of them ruled out the incorrect caloric fluid model. And so then the zeroth law was put in to essentially rule that out and show that that's, incorrect. But the way they talk about the zeroth law in the textbooks is really odd, to say the least. I mean, they don't really bring up that it was brought in to rule out a caloric fluid model and why that's important. They talk about it as if we can use a thermometer to determine equilibrium. I mean, I don't know. I don't get it. But we'll do it the way that I think is correct. So we're going to talk about the way they state this is that if system A, and this is one of those big things, is they're going to talk pretty much entirely about thermodynamic systems. And so we need to discuss what that means and then how that goes. And it's kind of a different new thing kind of stuff. And it's a little eerie because you can kind of do anything with these thermodynamic systems. I mean, it takes a little getting used to. The calculations we'll do are very straightforward, not terribly challenging. So I think that's excellent as our ending topic for the course. So if system A is in thermodynamic equilibrium, with system B, then what we get is that the temperature of A is equal to the temperature of B. And the system B is in thermodynamic equilibrium with system C. And the temperature of B is equal to the temperature of C. Then system A is in thermodynamic equilibrium system C. The temperature of A is equal to the temperature of C. And then you're like, seriously? Isn't this like the transitive property in math? I mean, this is what we were missing? How is this that important? Okay. And this is the general diagram that we have, is that we have our system A, and then we have our system B, and then we have our system C. and that this indicates that these are in, thermal contact. This, and so you see A isn't directly in contact with C, like so. And you're like, really, this is what was missing? The transitive property for temperatures. That's what's missing? And the answer is, well, what this indicates is that thermodynamic equilibrium is indicated by the temperature. Okay. And so if we go and we remember back to the caloric fluid model, then what they talked about was that objects that were hotter had more caloric fluid and objects that were cooler had less. And if you put them into thermal contact with one another, then it was like, osmotic pressure. You essentially transferred the fluid from the more to the less until you got equal amounts of fluid, and then you were in equilibrium. So equilibrium was equal amounts of caloric fluid. And then Joule showed that really heat was a transfer of energy and that it was not about a fluid. Okay, so he disproved the fluid model and stated that, oh, this is really some sort of transfer of energy. And so then the conclusion people said, well, that's fine. So this must just be that we have equal amounts of energy instead of fluid. So really the fluid was just the energy. No big deal. On we go. Except for the answer is no. Okay. So if you go in, we take like a hot cup of coffee in a cool room. Okay. And we calculate remember the temperature. Matter's made out of atoms and molecules held in place by electromagnetic bonds, and they sit there and they wiggle in place like little kids on sugar trying to sit still in seats. And the average kinetic energy of that wiggly random motion indicates the temperature of the object, or is a measure of the temperature of the object. Okay. And so when you go in and you look at that total kinetic energy contained in the hot coffee compared to the total kinetic energy in the entire room, there is more energy in the room than there is in the cup of coffee, even though the coffee's hotter and the room's cooler, because there's so much more stuff in the room than in the cup, then you have more energy in the room. And yet you transfer the energy from the cup to the room, from the little energy to the bigger energy. So this is not about amounts of energy. It is about the temperature until the average random jiggly motion in the coffee, the average kinetic energy of that jiggly motion is the same as the average kinetic energy of the random thermal motion in the room. It's the temperature that matters. It is not about the amount of energy. It is not about the amount of a fluid. It's not about any of those things. And so that is, in my mind, what the zeroth law says. And then the textbooks talk about how you can make a thermometer. So I just don't get it. But that's okay. Whatever.